All right, so you probably remember trig functions from math class, right? SOHCAHTOA, finding the height of a building. But what if I told you they're so much more than that? We're talking about the hidden language of the universe. Seriously, they describe everything from ocean waves to starlight. So today, let's dive in and see how these simple ideas became the absolute key to understanding the rhythms of the cosmos.
I love this quote. It really hits the nail on the head. Trigonometric functions transcended the concept of the right-angled triangle, playing a pivotal role in Fourier analysis, signal processing, and even quantum mechanics. That's the whole point right there. We're moving way beyond just triangles. We're talking about the fundamental tools scientists use to model basically anything with a repeating pattern. Think sound waves, radio signals, even the orbits of planets. It's huge.
Okay, so how on earth did that happen? How did we make this incredible leap from simple triangles to something as mind-bending as quantum mechanics? Well, like a lot of great ideas in math, the whole journey starts with a really practical problem. Just trying to measure stuff that's way out of reach.
And here's where it all began. The good old right-angled triangle. Early mathematicians figured out something super cool. For any angle in a right triangle, the ratio of its sides is always the same. So they gave these ratios names you'll definitely remember. Sine, cosine, and tangent. SOHCAHTOA. This was an absolute game changer for everyone from astronomers charting the stars to surveyors mapping out land. But there was a catch.
And this is the question that really broke things open. What does sine even mean for an angle of 270 degrees? Or what about a negative angle? Think about it. You can't have a triangle with an angle that big. The sum of angles is only 180. So the old definitions just fell apart. To unlock what these functions could really do, we needed a new, much bigger idea. And that breakthrough, the elegant solution to this problem, came in the form of the unit circle. It's such a simple concept, right? Just a circle with a radius of 1 plopped right at the origin of a graph. But trust me, this simple idea changed everything. It gave us a way to define trig functions for absolutely any angle you can think of. Big, small, positive, negative, it doesn't matter.
Okay, and here's the magic trick. We completely ditch the idea of opposite and adjacent. Instead, we start thinking in terms of coordinates. For any angle you pick, you just see where it hits the edge of the circle. That point has an x and a y coordinate, right? Well, guess what? The x coordinate is the cosine, and the y coordinate is the sine. Boom. Just like that, angles like 270 degrees or even negative 90 degrees aren't a problem anymore. They have a clean, simple definition.
So this new way of looking at trig functions, this unit circle thing, it has a really beautiful consequence. Because when you start to track what those x and y coordinates are doing as you go around and around the circle, well, you discover something pretty amazing.
If we just plot the y coordinate, that's the sine, remember? As our angle gets bigger and bigger, we get this perfect, beautiful repeating wave. It just flows smoothly up to 1 and down to -1, over and over again. It repeats its pattern every 360 degrees, or, as mathematicians often say, every 2 pi radians. And this wave, the sine wave, it's like the fundamental heartbeat of the universe.
So what about the other guy, the x-coordinate, the cosine? Well, it traces out a perfect wave too, but with one little difference. See how it starts at its peak at 1? That's because at an angle of 0, the x-coordinate is as far to the right as it can get. It's the exact same beautiful rhythm as the sine wave, it's just shifted over a little bit. It has a different starting point.
Now, if you look closely, you'll see a hidden symmetry in these waves. The sine wave is what we call an odd function. If you spin it 180 degrees around the center point, it looks exactly the same. The cosine wave, on the other hand, is even. It's a perfect mirror image of itself across that vertical y-axis. Now, this isn't just a neat math trick. These properties are super useful in the real world, like in signal processing, where engineers can use this symmetry to clean up messy signals and filter out noise.
Okay, so we have these waves, and they have some cool properties, but it turns out they also follow a strict set of rules. Think of them like the laws of physics for trig. We call them trigonometric identities, and they're basically the rule book for how sine and cosine behave and interact with each other. And the most fundamental rule of all, the absolute cornerstone, comes from a really simple question. What do you get if you take the sine of any angle, square it, and add it to the cosine of that same angle, squared? The answer, no matter what angle you choose, is always 1. Always. And why? It's just the Pythagorean theorem in disguise. Remember our unit circle? X squared plus y squared equals the radius squared. Since our radius is 1, it's just x squared plus y squared equals 1. Beautifully simple. And that famous rule is just the tip of the iceberg. There's a whole toolkit of these identities. You've got formulas for adding angles together, for doubling angles, you name it. These are the secret weapons that scientists and engineers use to tackle incredibly messy equations and simplify them down to something they can actually solve. Like in physics, they're essential for figuring out how different waves, like light or sound, interfere with each other.
All right, so we've got all these awesome tools for going from an angle to a value. But what if we want to go backwards? What if I tell you the sine of some angle is 0.5, and I want you to tell me the angle? That's where we need a whole new set of tools, the inverse trigonometric functions.
But right away, we hit a snag, a big one. Just look at the sine wave. If I ask what angle gives you a sine of 0.5, well, there isn't just one answer. There's one here, and another one over here, and another one. There are literally infinite answers because the wave keeps repeating forever. This is a problem. For a function to have a proper inverse, each output can only come from one input. So what do?
The solution is actually pretty clever, and it's basically a gentleman's agreement among all mathematicians. We solve the problem by restricting the domain. We all just agree to only look for answers within one specific slice of the wave. You can see it here. We just chop out a piece where the wave doesn't repeat itself. By focusing on just that one section, we guarantee there's only one angle for every possible value. And just like that, we have a perfectly well-behaved inverse function.
And here are the results of that agreement, the official rules of the game. For arc sine, we promise to only give back answers between -90 and +90 degrees. For arc cos, the answers will always be between 0 and 180 degrees. These are what we call the principal values. And this is exactly why your calculator doesn't just freeze up when you ask for an inverse sine. It knows this rule and gives you that one, single, agreed-upon answer.
Okay, let's take a breath. We've gone from triangles to circles, from simple ratios to these incredible waves. We've even figured out the rules they play by and how to go backwards. Now, let's put it all together and see why this is truly the language of science.
And this language is absolutely central to calculus, which is the math of how things change. And here's the mind-blowing part. It turns out the rate of change of a sine wave is a cosine wave. And the rate of change of a cosine wave is just a negative sine wave. They're literally describing each other's changes. This deep, incredible connection makes them the perfect tools for modeling anything that changes in a cycle. We're talking the vibration of a guitar string, the alternating current in your walls, you name it.
So, think about the journey we've just taken. We went from static, boring triangles to the pulsing rhythm of the entire cosmos. It's an incredible testament to the power of just following an idea. And it really makes you wonder, right? What other hidden patterns, what other secret cycles are out there, just waiting for us to find the right language to describe them? What other secrets of the universe are just waiting to be unlocked by the simple, elegant dance of sine and cosine?